Welcome to today's webinar brought to you by CelerData. I'm Stephen Fegg, Director at Database Trends and Applications and Unisphere Research. I will be your host for today's broadcast. Our presentation today is titled Go Pipeline Free with Real-Time Analytics. Before we begin, I want to explain how you can be a part of this broadcast. There will be a question and answer session. If you have a question during the presentation, just type it into the question box provided and click on the submit button. We'll try to get to as many questions as possible, but if your question is not selected during the show, you will receive an email response. Plus, all viewers today will be entered for a chance to win a $100 Amazon gift card just for participating. Now, to introduce our speaker for today, we have Sida Shen, Product Marketing Manager at CelerData. Now I'm going to pass the event over to Sida to get us started. Welcome to the broadcast, Sida.
Hey, Steve. Can you guys hear me okay?
Absolutely.
Okay. So let's get started. Hey everyone. My name is Sida Shen, and I am a product marketing manager here at CelerData. And today we're going to talk about real-time analytics, right? And I'll explain what is the methodology behind the pipeline-free real-time analytics approach, and mainly talk about what is wrong with doing denormalization in real-time analytics, right? And then we're going to go into how do we actually achieve pipeline-free real-time analytics. And we'll take a look at the open source real-time OLAP database, StarRocks. And then I will do a demo on the CelerData Cloud. It is a cloud offering of StarRocks, and show you guys exactly how a query is planned and is executed, right? And it's going to get a little technical, but I promise it's going to be very fun. Okay. And, from the beginning, like in the 1970s, when database management system was invented, it's always been a good practice to keep your data in a multi-table schema, right? Whether in a Snowflake schema or in a star schema, or, data, in natural, it is relational, right? But this is not really the case anymore, especially for real-time analytics, right? Because a lot of the real-time OLAP databases simply cannot really handle on-the-fly joins well with low latency. So the database actually requires the users to perform denormalization before ingesting the data into the database, right? So everything becomes single table. So denormalization, what it is basically you, like say you have table in star schema, right? Let's see 5 tables here, and you perform a pre-join into a flat table, right? And this process is probably okay for batch analytics where, the freshness of the insight can go from like hours to even days, right? You do a big batch every few days, and that's okay. And you have the time to do the denormalization in batch. But in real time, with the time constraint, that's not really the case, right? And you need to turn to stream processing tools and create like stateful stream processing jobs to do denormalization. And that can be a very expensive process, both in terms of the architecture, right? So you need to maintain an infrastructure level processing tool in your real-time data pipeline. And that is expensive by itself. And doing denormalization in a streaming fashion, like with a stateful stream processing job, and that can be very difficult, technically very difficult, and it can be kind of unstable, and it's going to be very difficult to maintain, right? And this is the expensive part. But also doing denormalization also locks your data in a kind of like a single view format. So it's really difficult to change after everything's all configured, right? And when you before you configure your denormalization pipeline, you need to actually know the query pattern beforehand, before configuring the pipeline, right? And after it's configured, if you want to do, say, a schema change on one of the source tables, right? And you have to actually reconfigure the entire pipeline. and backfill all of the data into your denormalized table. And that can be very time consuming, very resource intensive, and just very expensive in general. And in business, changing a metric or changing a column or adding a column in your source table is not really a big ask. But in real-time analytics, when doing denormalization, and this can be a very expensive operation, right? So how do we solve this, right? And this, just do on-the-fly join. So this is a lot of the reason, a big part of the reason why we started the StarRocks project, right? It's because we kind of saw this kind of issue that the users are suffering when doing real-time denormalization, and that's why we built the StarRocks project, right? And I'll go into deeper into the technicals, architectures about why StarRocks can perform joins on the fly really well. But in the beginning, I want to kind of show some numbers first, right? And here, first, let's take a look at some benchmark results, right? And this is like the SSB benchmark test. So SSB benchmark test actually has two variants. The first one is the original SSB test. It's multi-table. It has a few tables, and the query test is actually on-the-fly join. So you on-the-fly join everything, right? And ClickHouse, the folks at ClickHouse actually made another variant of the SSB benchmark test, where they did a denormalization of the SSB benchmark test, the tables, pre-join all of the SSB tables into one big table, and do all of the queries on that one single table. That's why you see on the right-hand side, there are the ones that with a flat in the end, and there are the ones that, not ones, but StarRocks with multi-table in the end, right? And if you see the result, you can see that StarRocks is the fastest on the flat schema SSB benchmark test. So it is way faster than Druid and around like 2 times the performance of ClickHouse. But the key thing here is a multi-table test, right? To compare multi-table result with the flat table result is really not a fair comparison, because no matter how you put it, join is still a very expensive task, expensive job, right? And actually StarRocks multi-table performance on the same data set, not on the same data set, but on the same queries with the same hardware resource is faster than Druid's single table, and it's almost as fast as ClickHouse single table. So this alone, we can say that StarRocks is able to kind of eliminate denormalization, right? And without really much losing anything. Yeah, the performance is a little slower, but our architecture actually ensures that you add more nodes into the cluster, and the query performance actually scales up like near linearly, right? And I'll go into the technical architecture in a bit. Because StarRocks has such good query performance on query performance for like complex OLAP style queries, and actually we brought StarRocks to the data lake. We started working that like 1.5 years, 2 years ago, and it actually works on the data lake. And this is a benchmark test of TPCDS to actually showcase how good StarRocks is on multi-table queries. And TPCDS is kind of different than SSB. If say SSB really resembles the kind of workload reports and dashboards, right, where the queries is not really that complex, and the queries is always generated by some kind of application or some BI tools. So it's not really that crazy, right? It's multi-table, but it's not really that complex. TPCDS really resembles those queries that data scientists write, like those ad hoc queries, very complex ad hoc queries, and those kind of ETL kind of workload. So the query is much more complex than the ones with SSB multi-table schema, right? And Trino is a open source query layer, query engine for the data lake that is pretty known for its high performance on the lake, right? And here, StarRocks querying the same data in the data lake is actually 5 times faster, 5.5 times faster than Trino on the data lake, with a kind of more extreme query pattern and very complex queries, right? And I'll go into how we done this like later in the slides. And let's look at some case studies first, right? And Airbnb's Minerva Minerva project is like a metric management platform. It holds like 7,000 metrics and has 6+ petabytes of data in it, right? Before they met StarRocks, they were using Apache Druid and Presto as their query layer, mainly Druid. And they store a lot of their data in Druid because a Druid doesn't really do join that well, or doesn't really do it at all. So what they needed to do was they needed to denormalize everything on 6 petabytes of data. And that's pretty expensive, right? And the thing, like the biggest pain point actually for them is schema change. A metric platform changes a lot because it has a lot of metrics in it. Like changing a metric is very normal for Airbnb. But on the technical level, it's not a small ask because they needed to not only change the schema, they needed to change the whole denormalization pipeline, and as well as backfill all of the data for the flat tables. And this process, according to them, can take somewhere from the hours to even days to do. And hours to days is really not acceptable for a company like Airbnb. It doesn't really satisfy their needs, right? So they're looking for alternatives. They say, denormalization, what if we can just do joins on the fly, right? And that's when they discovered StarRocks. And after they incorporate StarRocks and find out, joins can actually be done on the fly. So by ditching Druid and Presto and going into StarRocks, what they did was there's still some tables that are denormalized, but majority of the tables are on the fly join now. So according to a webinar they actually did with us, they said that with StarRocks, denormalization is only on demand for those very extreme, highly concurrent workload, and by default, all of the tables are normalized and stay the same schema as the data source, right? And so this is huge for them because by having the same schema between your OLAP database and the data source, there's really everything streamlined. So there is no more data backfilling. There's no more configuring stateful pre-processing, stateful stream processing jobs. And there is no more like reconfiguring the pipeline. And everything was so much cheaper, and even with better performance in their case, right? So how do we do it? So how do we achieve this kind of performance on joins, especially when compared to other kind of real-time OLAP databases, right? And here we're going to take a deeper look into StarRocks, the open source OLAP database StarRocks, and it's going to get a little bit technical, but I think it'll be okay. Right? And first, let's take a look at some like higher level compute architecture differences, right? And the first type is what we call is scatter gather. So this kind of architecture is you have some sort of task, right? And you distribute the tasks to a bunch of nodes, and the nodes return some kind of intermediate result to a larger node, and that larger node does the final calculation. And this kind of architecture is really easily bottleneck on a single node. So what it means for join operation, especially in a distributed environment. So all of these three are distributed way of computing, right? Do distributed computing. And for distributed computing, so for distributed join, the biggest difficulty is actually, so how do we distribute the data that we're trying to join together into all of the nodes as possible, right? And for a scatter-gather model or other OLAP databases, real-time OLAP databases, they simply do not support the shuffle operation, right? It does not like do data shuffling. So all they can do is broadcast join. So broadcast join basically means you broadcast your smaller table to all of the bigger tables and one node per copy. And that doesn't really scale well, right? The bigger your cluster, the more you need to broadcast and the more memory it's going to use. It's not only depend on your data size, also depend on the size of the cluster. So that's not really scalable. That's not really like truly scalable distributed join, right? Because shuffle operation is really rarely supported for those databases, right? And the second type of architecture is kind of like map reduce. You see that with Hadoop and variant like Spark, those ETL tools, right? And so they have operators, and each operator, they implement a map and a reduce, right? And each intermediate result is persisted to disk, right? And because they do a lot of like ETL jobs, and join is necessary, right? And they support shuffling, but the shuffling service is always, like all of the intermediate results are persisted to disk. So the performance for low latency is definitely not satisfactory. And for these kind of architecture, it's really good for those ETL jobs, right? Because everything is persisted to disk, and the fault tolerance is good. So when the query fails, you can actually go back to the last checkpoint because everything is persistent, right? And so this kind of architecture is not really good for low latency, but it's very good for ETL jobs. And then we go into this kind of pure in-memory MPP architecture, right? And this is actually the architecture StarRocks is on. So it supports, it streamlines the query execution. So there is like no wait time before different tasks in it, because nothing is really persisted on disk, right? And it also supports data like in-memory data shuffling. So our operators or our nodes can actually communicate each other, through a shuffle task. And so this actually enables, this is the biggest reason that why we can enable really high performance scalable joins on a larger scale, right? And this is a higher level architecture. And a query, you run a query is like on the highest level is like a two-phase process, right? So the first part is query planning. So you actually need to figure out what the query is trying to say and come up with a plan and send it to your executors, your compute nodes, and the compute nodes actually execute the query and return the result, right? And query planning is a very important piece because the difference between an optimized query plan, distributed query plan, and an unoptimized query plan can be several orders of magnitude big, right? There are sometimes customers that come to me with a query, and because the plan is not optimal, sometimes the difference is between like thousands of times, and something like that is pretty normal, right? And doing optimization, doing optimizer, this like choosing different like drawing strategies and drawing ordering and what kind of aggregation method we use, is one stage or two stage. There's search space for possible ways of executing like a query, especially an OLAP query. It's enormous. Like doing like only just say drawing ordering, that's a NP problem, right? NP stage problem, right? And so that's the reason we spend a lot of time building our own cost-based optimizer. So what a cost-based optimizer is actually collect statistics from the data and use that data to estimate the cost of each plan and thus selecting the best one, right? And this sounds simple, but it's really actually not. It requires a lot of optimization. And StarRocks cost-based optimizer is actually natively built because any optimizer needs to be very deeply integrated with the execution and the storage layer, right? So you cannot really just take something that's open source and slap to any database and expect it to work, right? And StarRocks cost-based optimizer is actually it's been iterated for a pretty long time. Thank God we're open source. So we've been when it first released, it wasn't even on by default. And we worked with our seed user for almost like a year to make it optimal. So that was a long process. And it's a feature that works now. And it's one of the biggest reasons that StarRocks is very good at joins, on-the-fly joins. Right. And then let's take a look at query execution, right? So StarRocks really features a columnar storage plus like fully vectorized operator. So query execution operators, right? And this is not really specifically for joins. And this is mainly the reason why StarRocks is fast overall, not only for joins, but for aggregations, large-scale aggregations as well. There's all OLAP queries, right? So what columnar storage means is that instead of storing data in rows, we store them in columns. And what vectorized operation means is that in memory, we process everything by columns, right? And this is very good for OLAP workload because OLAP workload, you always take things by column, and by performing everything in column, we get bigger batches, right? So it's a lot easier to incorporate a lot of SIMD optimizations. I'll talk about this in the next slide, right? And because StarRocks is C++, like our execution engines is purely C++, so we're able to kind of utilize a lot of the SIMD instruction sets to accelerate our queries, right? So what SIMD actually means, like for database, is basically we can process multiple data points with one instruction, right? So there is a lot less memory seek when doing it, right? So the figure above here, I'm not sure if you guys can see my mouse, but the figure above here is kind of like scalar operation, right? So you have two vectors, you perform addition, and you return another vector, right? So you actually have to go into the memory and get each one of the data point, add them one together, and then return all. So there are actually, that's how many? That's 12 memory seeks, right? But with the SIMD addition, there's only 3. Get the vector, get the second vector, and return the result, right? And this way, it's a lot faster. And StarRocks query engine, actually, all of the operators, we do them as many as possible. I think now, like almost all of them are SIMD optimized. That's with like filtering or parsing or joins, aggregations, all of the operations, right? And this is actually why StarRocks requires AVX2 instruction set. And that instruction set is a SIMD kind of instruction set, right? Okay, let's go to the next page. Yep. And okay, so on the fly joins, we can do it. But join is still a very expensive operation. No matter how you put it, no matter how, it doesn't really matter like how optimized your query layer is, it's still a very expensive operation, right? And for when I see customers, some of my customer has tens of thousands of QPS, and doing on-the-fly join is really not an option, even with a database like StarRocks, right? So what do we do? And the answer is actually pretty simple. So instead of doing denormalization in a pre-processing or a stream pre-processing tool, we can actually support a partial update operation directly on the columnar storage, right? So what it means is that so you can have one stream of data, say from Kafka, and another stream of data, and the two stream can perform data upsert to the same table at the same time, right? So that's like doing denormalization within the database and doesn't really require a lot of computation and doesn't require another processing tool that's outside to do that, right? And this is easier said than done. And there are a lot of different optimization involved in this. But this is a feature we've been working on a long time to let our users to actually go pipeline free and get rid of all of the denormalization that's beforehand, right? Okay, so we talk about StarRocks, and I'm from CelerData, and we are actually the maintainers of the StarRocks project, the StarRocks open source project. And we actually have a offering for StarRocks, a cloud offering for StarRocks, CelerData Cloud. Right. CelerData Cloud is completely based on StarRocks, so it has all of the good performance, but it also takes care of the maintenance job for you, right? So how it operates, it actually operates in a BYOC kind of fashion. So bring your own cloud. So instead of deploying the database in our VPC, we actually deploy it in your VPC, and there is a management service in our VPC that help you do all of the database management and sort of things, right? And there's a SQL editor I'm going to show. And the reason why we do this is for the absolute maximum security for you, because you own your own deployment and you own all of the data that you have, right? And I'll do a little demo here, and I'll showcase what the cloud looks like. And here I want to share my screen. Can you guys see my screen? It should be CelerData Cloud with one Chrome window.
Looks good.
Okay, good. And yeah, so here is CelerData Cloud BYOC, and that's the name. And yeah, so you can see here, I already have a cluster that's here. I created that last week for a demo, and it's on version 3.0.3, and that's the StarRocks version. So it's actually having StarRocks running the backend, and you can see the cluster size I have here. I have one FE node. So the FE node, StarRocks, the CelerData FE node is the one that take care of all of the query planning, the cost-based optimizer we talked about earlier, right? And the node type. And actually, we have a pretty small cluster, so we only have 3 nodes, and with a 4x large MCI, right? And it's all good, up and running. And here I want to showcase some capabilities of CelerData Cloud, right? First, it actually has a role-based access control. So you can create a role and give it permission. We have, that's how many? That's like 10 privileges you can attach to your role, and you assign, the role to your users. So it's very easy to perform access control, right? And you can also customize your alarm policies. So, based on the cluster's disk or memory utilization or CPU utilization, a lot of things, right? And because it is on the cloud, so we charge everything by the second. So we have a pay-as-you-go kind of structure, and also a 30-day free trial. This account is relatively new. I'm still on the free trial. And yeah, and the usage is calculated by the consumption unit. And this is by the second too, right? And also there's something that's pretty neat, and we just built. And you can actually, we have open API keys. So you can actually build your own application and take this key to control the whole cluster without logging into the console and do it from your own application, right? And then let's take a look at what's inside. Okay, let me in. Good. And okay, so let me kind of explain what is going on here, right? So you can see I have a database called TBCDS 1 terabyte. So before this webinar, I was actually thinking, so how do we showcase join capabilities? The easiest thing to do is to, load the TBCDS 1 terabyte data set, like I showed before, and actually show the query running live. But that's kind of boring, right? Because I already showed the benchmark. And here is actually one thing I want to kind of explain. So, like for running an OLAP query, like a very complex OLAP query, right? So the biggest thing you want to do is to minimize the amount of data that your CPU process, right? And like for a lot of the database, they can do predicate pushdown, which means that you have a where clause on the table and that gets pushed down to the storage layer, so it doesn't scan all of the data, so your CPU doesn't get all of the data, right? And this is a simple concept, but in a lot of scenarios, it works very differently, right? And we actually have a feature called global runtime filter, and I'm going to use a TBCDS benchmark test with some queries, and we can actually show how a query is planned and executed from our console here, right? Okay, let's take a look. So these 4 tables are the tables I am interested in for those queries. Let me show them first. So the first one is store sales. And this is, I think, the biggest table in TBCDS. For 1 terabyte, it has 2.87998 billion rows. That's a lot of rows. And we have a customer table. A customer table is, I think this is 12 million rows. And we have an item table that's a bit smaller, 300,000 rows. And we have a call center table that's only 42 rows, right? And we're going to write some SQLs, look at some SQLs. These are the SQL I just wrote, and take a look at how we handle the problem of, decreasing the amount of data that hits your CPU, right? So the first one is pretty simple, right? And you have a store sales table. So the biggest table join with another table, right? On the join key. And you have a predicate. This predicate here is actually the same as the join key. So this predicate is in this table as well as it is in this table, right? So this is a very simple case. Yeah. And then we can take a look at the query profile. Yep, it takes a little time. Yeah. And here is a CelerData kind of query profile page. So you can see exactly how a query is run, right? And the scan took a long time. Let's take a look, right? We actually put this is the customer tables predicate, and StarRocks actually sent this predicate to the other table, right? You can see here, right? And this is a table for store sales. And we send this predicate to so this is a simple predicate rewrite, right? So we can minimize the amount of data that's being scanned here, right? And this is the first one. And this is not really that complicated, right? So to send a predicate over, because this column is shared between the 2 tables, so the only thing we need to send is basically this predicate. We don't have to create an actual like a Bloom filter or some sort of other data type that with the thing that we actually want to filter. We just send this, and it's cheap, right? But what if this predicate is on some column that is not in this table, and this becomes a much more difficult task to solve, because is sending this whole predicate worth the while of like filtering the bigger table? This is actually what our global runtime filter, this feature does, right? And let's run this query and take a look. Oh, think I broke something. It's a pretty big data set. It's going to take a while. Okay, let's take a look at the query profile, right? Let's scan now. See, so this is, you can see our global runtime filter in action, right? And the table is 2.7 billion rows, right? And the input is 2.7, but the output is actually only 300 million. So this predicate, despite it's not being in the store sales table, it's still, we recognize this, and we somehow eliminated this from the query execution, right? And if we say here, okay, the rows, the raw rows red, this is the overall number of rows that's in the table, and this is actually the number of rows that's red. And this is expected because in this case, we still scan all of the data, but the runtime filter actually eliminated 90% of the data at query execution. Between the nodes, a Bloom filter is sent from the smaller table to the bigger table. So the operators actually, during query execution, like 90% of the data is actually didn't get calculated, right? And that's why this query can be run in 5 seconds. By 5 seconds with such big amount of data and with a relatively small cluster, right? And there are other ways to do it. And the reason why it didn't get pushed down to the storage layer, this predicate, the storage layer of the bigger table, the store sales table, is because our optimizer think it's not worth it, because this predicate is still pretty big. I mean, like item equals category. I think this is a 30,000 row result, and sending the 30,000 rows to the bigger table, to all of the nodes, our optimizer think is not worth it. Now let's look at this like smaller. This is a very small table, right? And this is a smaller result, and this is going to get pushed down to the storage layer. Let's see the result. Okay, so here you can see that actually during query execution, input row is only 5 million. And you take a look at the rows that's being read. So the total number of rows is still 2.87 billion rows, but the rows that's being read is only 5 million here, right? And this actually showcases how smart our query planning is. It can change its strategy based on the underlying data, right? And this is really a cost-based kind of approach of optimizing a query, right? And so this is our global runtime filter. I hope that wasn't too confusing. If you have a question, please raise them. And yeah, and because StarRocks is so fast, right? It's fast with its own storage engine, and it can do query planning very well, right? And so we actually brought that performance to the data lake. And StarRocks has this feature called a data catalog. You can use it to, so a catalog basically is a kind of like a metadata manager, right? You have a default internal catalog that's the StarRocks own metadata management tool. And you can actually add in external catalog and connects to different data lakes like Apache Hive, Iceberg, Hudi, Delta Lake, and we support Pymon and many others, right? And let's just connect to a AWS Glue with data on S3, right? Let's name it Glue Catalog. And region, my data is in Oregon, US West. And my AWS Glue region is still in Orga, right? And because we're using Glue, the default format is Hive table format. So there's that. Next step, I already done all of that. We're gonna use instant profile based authorization and create a catalog. Just by doing that, you have access to the data on your data lake, and this in this case is data on S3 on an S3 bucket with metadata managed by AWS Glue, right? And here I can take a look, and we can actually show all of the tables that's from the Parquet file done. See? This is all of the tables from the Glue catalog that I just made with a few simple steps, right? And we can actually use this as our database, our default database. See, and we can select count the number of source cells, because what we're doing here is actually we're reading the data that's on S3 right now. And that's the same table, but a very different data source. And this is on the data lake. And StarRocks can not only be used for real-time analytics, like with its own storage engine, real-time capabilities. It can also be used as a query layer on the data lake and get much faster performance than other solutions on the market. Right? And okay, so here is my demo for the CelerData Cloud BYOC. Hope you guys liked it. And while we're still screen sharing, I want to show you some other stuff, right? And so this is the StarRocks project, and you can go take a look. And we have 5.3 stars. Give us a star, and it's completely free, so you can look at the source code and download the binary and try for yourself. And to do a quick start on StarRocks, it's pretty simple. It's a Docker run. A simple Docker run can get you started and experience a very good join performance, right? And you can also go to our website, CelerData.com blog, and we have a tons of blog that covers user-facing analytics, data lake, and real-time analytics, and how to decrease your costs for real-time analytics, and how to get started on real-time analytics, right? And this is a good resource too. Right? And yeah, I think I'm good here. Let's stop my screen share. And yeah, and thank you for watching the demo. And this is all I have. And here are some resources. So CelerData blog, how to sign up CelerData Cloud. You can sign up today to get a 30-day free trial. And you can join our Slack channel here. And our GitHub just showed, and you can always connect with me through email, c.shen@celerdata.com, or you simply go to c.shen.com, and that's going to take it to my LinkedIn profile. Right? And this is all I have. Back to you, Steve.
Thank you very much, Sita. Okay, we're going to dive into questions from our viewers today. First question, how does real-time analysis impact decision-making and operational efficiency?
Yeah, so yeah, for real-time analytics, it's really based on your own use case, right? And if you're doing something like fraud detection, having data there in real time and being able to query sub-second is very important, right? Because you want to catch the frauds in real time, right? So I think the right answer is you first have to analyze your own use case, and is doing real time actually worth it for you? Because the cost of real time has decreased a lot over the years, because more solutions that come out, it's still some overhead with real time analytics, right? You have to use different tools, and practice is a little different, right? So before going into real-time analytics, I think the question for you to ask yourself first is my case going to benefit from going real-time, right? And it's different for every single business.
Understood. Next question. What are the reasons that StarRocks is faster than Trino?
Yeah, so faster than Trino actually. Trino can do joins pretty well. I think it's the reason. I'm not sure if I can go back to the slides. Yes, you guys can see the slide, right? So this is basically the reason. So StarRocks can do, it's built on C++, and Trino is not built on C++. It's written in Java, right? And so we can utilize all of the SIMD instructions that can be very beneficial for large scale OLAP queries, complex OLAP operations, right? And to pit it against Trino. And this is mainly the reason.
Understood. Thanks, Sita. Okay, next question. Can StarRocks perform real-time data updates?
Yes. StarRocks actually has a primary key index. And so in the industry, a lot of other solutions do merge on read for data update, which means that the data is written into different versions and it's being compacted, into one in the background job, right? And that's very harmful for query performance. Actually, if you do that, the volume is higher. But we have actually a primary key table, a primary key index that we can do merge on write. So all of the data upsert, we can handle those at data ingestion. So it doesn't really compromise the query performance at all. And yes, it supports data upsert natively. And with our own storage engine, you can do them on a pretty high volume and pretty frequently without hammering your.
Got it. Okay, moving on to our next question. What data lakes does StarRocks support as a query engine?
Yes. Yeah, so good question. So StarRocks supports Apache Hive, Apache Iceberg, Delta Lake, Hudi, and Pymon. And that's the main kind of data lake table formats that are supported.
Got it. It looks like we're through our attendee questions for now. If anyone else viewing has any questions, please send them over. But in the meantime, Sita, if there's one thing you'd really like our audience today to walk away keeping in mind, what would that be?
Yeah. So so go pipeline free. So if you're using real-time analytics, or you're thinking about using real-time analytics, just to know that denormalization is actually something we can avoid. You don't have to suffer through that, because innovative solutions like us and actually some others can do joins, and like very good performance joins on the fly. So you don't have to do denormalization.
Fantastic. Well, I would like to give a huge thank you to our speaker today for coming on board and sharing his insights and expertise. Once again, Sita Shen, Product Marketing Manager at CelerData. If you in attendance would like to review this presentation or send it to a colleague, you can use the same URL that you used for today's live event. It will be archived, and you will receive an email from us once that archive is posted. And again, as I mentioned before, just for participating in today's event, you could win this $100 Amazon gift card. The winner will be announced on August 31st. We'll reach out to you via email if you are the lucky viewer. Thank you, everyone, for joining us today, and we hope to see you again soon.